For hundreds of years, the cosmos was a purely theoretical space. We mapped it through the glass of early telescopes and defined its rules using the complex equations of celestial mechanics. But understanding the math of the universe and actually leaving the Earth are two very different things. Escaping gravity requires a massive mobilization of resources, and for a long time, humanity simply didn't have a compelling reason to foot the bill. That reason arrived in October 1957, when the Soviet Union put the Sputnik 1 satellite into orbit. Space immediately became a domain of active military and political competition. Orbit was now a high ground to be captured. Driven by intense Cold War rivalry, the United States and the Soviet Union poured vast fortunes into rocketry. This geopolitical sprint forced an explosion of engineering progress, culminating directly in the Apollo 11 lunar landing a little over a decade later. Pitting superpowers against each other successfully put boots on the lunar surface. However, relying on multi-billion-dollar rockets that were thrown into the ocean after a single use was an incredibly expensive way to explore. It was a model designed for political victories, not long-term habitation. As the space race cooled, the strategy shifted toward international cooperation. By 1998, former rivals began assembling the International Space Station. The goal shifted from planting flags to learning how to keep humans alive in the vacuum of space. Living in microgravity takes a severe toll on the human body, specifically causing rapid muscle atrophy and bone loss. The core scientific mandate of the ISS has been to document these physiological changes and test biological countermeasures so that crews can eventually survive longer trips. While these biological limits kept humans anchored in low Earth orbit, our machines ventured much further. Robotic probes like the Voyager spacecraft were sent out to map the complex environments of the outer planets. Today, machines like the Perseverance rover continue this work. They operate as our robotic scouts, dynamically analyzing alien terrain and chemistry to pave the way for a physical human presence. We had proven that long-term survival in orbit was technically feasible, and that we could navigate the solar system. Yet the astronomical cost of relying solely on government-funded programs kept space out of reach for widespread expansion. For over 50 years, the standard approach to spaceflight involved a massive financial penalty. After millions of dollars and months of construction, the launch vehicle was intentionally discarded after a single flight. Then, in 2015, SpaceX recovered an orbital-class booster. By successfully landing the rocket back on Earth, they proved that hardware could be flown again. This chart shows the historical cost required to reach orbit. For decades, the financial baseline remained stagnant, demanding hundreds of millions per launch. But reusable boosters caused a massive disruption. By recovering hardware, the price per launch dropped sharply to roughly $62 million. This lowered barrier to entry allows the private sector to step in. Anticipating the retirement of the ISS, commercial companies are now actively developing their own independent orbital habitats, like the Haven 1 station. By fixing the economic equation of getting to space, the domain shifted. What was once an exclusive theater for rival nations is now becoming a scalable, self-sustaining commercial economy. That commercial capability is now merging with renewed national ambitions. In April 2026, the 4 astronauts of the Artemis II mission launched on a lunar flyby, demonstrating that humanity is actively executing its return to deep space. This 10-day journey was a strict engineering test. It pushed the Orion spacecraft's heat shield and life support systems to their limits, ensuring the hardware is ready to support permanent bases near the lunar South Pole. To maintain those permanent outposts, crews will need to rely on in-situ resource utilization, or ISRU. This is the practice of harvesting local materials for survival, which is necessary to sever our total reliance on Earth-based supply chains. We are already testing this concept. As this diagram illustrates, the MOXIE experiment on the Perseverance rover successfully manufactured breathable oxygen by pulling it directly from the carbon dioxide in the native Martian atmosphere. Alongside this physical expansion, our observational reach continues to grow. Instruments like the James Webb Space Telescope are currently staring deep into the universe, piecing together the invisible filaments of dark matter and refining our understanding of cosmic expansion. We now have decades of biological data from the ISS, reusable rockets that make space launches affordable, and the Artemis infrastructure pushing us back to the moon. The combination of these tools proves that humanity is actively crossing the threshold to become a multi-planetary species.